Hello and good day. I'm Mason. I'm joined by Justin, Batuz, and Karthik. For our ECE 20001 final project submission, we have chosen to put our focus on a simple AC to DC full bridge rectifier due to its incredible significance in our everyday life. Next, I'll go over a general overview of the circuit, but we will also include in more detail the circuit's overall functionality and how key components each contribute to the final purpose of the circuit. Here we see the circuit diagram for our full bridge rectifier circuit with 4 diodes which convert AC to DC with a capacitor on the output to help smooth everything out. However, we'll have more detail on that later. We also have a 1K resistor standing as an example load in the circuit, but keep in mind that could be replaced with just about anything you would like. Before going into further detail though, you might wonder why this circuit is useful and where it is used in the world.
So full-wave bridge rectifiers are most generally found to be used in electronics such as car alternators, cell phone chargers, laptop tablet chargers, power banks, or lead battery chargers. As we can see, they're mostly used in electronics and electrical tools, which are mostly rechargeable items. And the reason why they're used in those items are because electricity are often transferred across long distance through AC current, as they're more efficiently transferred at large voltages, and AC current can more easily be reduced to a safer household voltage through the use of transformers. However, most appliances these days uses DC charging as it is much faster due to how there's less resistance for the current of electricity. So therefore comes the need to convert AC currents to DC currents.
Okay, and now we are gonna discuss functionality of the diodes. So diodes let current go in just one direction. This is because the diodes are made of a PN junction, which is an interface between two types of semiconductor materials, P-type and N-type, inside a single crystal of semiconductor. This means that the current can flow really well in one direction and is blocked in the other one. On the picture, we can see that when we connect a sine wave from, for example, function generator, and we have positive voltage in here, the current will go in this direction with this green arrow. It will go here and will be blocked in here, and then continue to V out. And here we have plus. And our minus, yes, it will go in the other direction than the red arrows. So it will go in this direction here and go to the minus. And when we change our signs in here, and let's say our plus is in here, it will again go to the diodes, will be blocked in here and go up with this arrow. And as we can see, our V out plus is in the same place. And similar situation with minus. Yes, it will go in the other direction than this red arrow, will go through this diode and again to the same place.
Now to talk about the functionality of the capacitor in the circuit. Although the output from an electronic rectifier circuit is technically direct current because all of the current flows in the same direction, it isn't suitable enough for most purposes. Even full wave and bridge rectifiers produce direct current that pulses in rhythm with the 60 Hz AC sine wave that originates with the 120 VAC current that's applied to the transformer. And that pulsing current isn't suitable for most electronic circuits. That's where filtering comes in. The filtering stage of a power supply circuit smooths out the ripples in the rectified DC to produce a smooth direct current that's suitable for even the most sensitive of circuits. Filtering is usually accomplished by introducing a capacitor into the DC supply circuit. Here, the capacitor is simply placed across the DC output. This is because of the capacitor's ability to store charge when the circuit load does not need it. Hence, the capacitor filter is used for smoothing and reducing the ripple content in output waveform. Apart from this, following are equally important functions of a filter capacitor. Number one, it improves transient current response. Larger the capacitor, better it will cater to the transient demands of the load. Transient current is current spikes. It improves voltage regulation of the power supply. Now is a good time to also introduce what the ripple rejection ratio is. This is the ratio of the ripple voltage that appears on the output voltage when the ripple voltage component, that's the noise, is superimposed on the input voltage to the input ripple voltage. The larger this value, the smaller the ripple component that appears in the output. That's it.
And these are our sources used to create this presentation.